Welcome to our comprehensive lecture on measures of central tendency and dispersion. These fundamental statistical tools are essential for anyone working in public health, epidemiology, or health research. These measures fall into two main categories. Central tendency measures help us understand the typical or average value in our data, while dispersion measures tell us how spread out or variable our data points are. These statistical measures are fundamental to public health practice. They help health officials make informed policy decisions, assess population health status, ensure research validity, and communicate complex health data to stakeholders and the public. Recent global events have highlighted the critical importance of these measures. COVID-19 data analysis has extensively used central tendency measures in vaccine effectiveness studies, while health equity research increasingly focuses on dispersion measures to identify and address health disparities across populations. Throughout this lecture, we'll explore each of these measures in detail, understand their practical applications in public health research, learn how to choose appropriate measures for different types of data, and examine current trends in health data analysis. Let's begin this essential journey into public health statistics. Statistical measures of central tendency and dispersion play a critical role in public health, serving as the foundation for evidence-based policy decisions and rigorous research practices. Health officials rely on statistical measures to transform raw health data into actionable insights. This process begins with data collection, moves through statistical analysis, and culminates in informed policy decisions. For example, mean vaccination rates help determine where to allocate limited vaccine supplies. Disease incidence patterns guide intervention priorities, and variations in health outcomes inform the design of targeted programs for specific populations. Population health assessment relies heavily on statistical measures to understand disease burden and health trends. This global burden of disease data shows how statistical analysis reveals changing patterns in mortality, chronic diseases, and risk factors over time. In research, statistical measures are essential for ensuring validity and accurate interpretation of study results. Proper use of central tendency and dispersion measures helps researchers draw reliable conclusions and ensures their findings can be reproduced and trusted. Effective communication of complex health data relies on statistical summarization. By converting vast amounts of raw data into meaningful measures like means, medians, and standard deviations, public health professionals can clearly communicate findings to diverse stakeholders, including policymakers, healthcare providers, and the general public. These statistical measures serve as the bridge between complex health data and actionable public health decisions, making them indispensable tools for modern public health practice and research. Central tendency measures are fundamental tools in statistics that help us describe the typical or central value in a data set. Rather than looking at every individual data point, these measures give us a single representative value that summarizes the entire collection of data. There are three main types of central tendency measures, each providing a different perspective on what represents the center of our data. These are the mean, median, and mode. The mean is the arithmetic average, calculated by adding all values and dividing by the number of observations. The median is the middle value when data is arranged in order. The mode is the value that appears most frequently in the dataset. Each measure has its own strengths and is suitable for different types of data and situations. The choice of which measure to use depends on the nature of your data and what you want to communicate about it. The relationship between these measures can tell us important information about our data distribution. In a perfectly normal distribution, all three measures are equal. However, when data is skewed, they provide different values and insights. Understanding these three measures of central tendency is essential for effective data analysis in public health. In the following sections, we will explore each measure in detail, including their calculations, applications, and when to use each one appropriately. The mean, also known as the arithmetic average, is one of the most fundamental and widely used measures of central tendency in statistics and public health research. There are two main formulas for calculating the mean. depending on whether we're working with an entire population or just a sample from that population. Let's examine these formulas more closely. In the population formula, N represents the total number of items in the entire population, while in the sample formula, N represents the number of items in our sample. Here's a visual comparison of both formulas side by side, showing the key differences between population and sample mean calculations. Let's work through a simple example to see how the mean is calculated in practice. Suppose we have the following blood pressure readings from 5 patients. To calculate the mean, we first sum all the values. 120 plus 135 plus 118 plus 142 plus 188 equals 643. Next, we divide this sum by the number of data points. Since we have 5 readings, we divide 643 by 5 to get 128.6 millimeter Hertz as our mean blood pressure. Here's how this calculation might look in a practical spreadsheet application, showing the systematic approach to computing the mean with real data. It's important to note that the mean is sensitive to outliers, extreme values that are much higher or lower than the rest of the data. This sensitivity can sometimes make the mean less representative of typical values in skewed distributions. Understanding the mean and its calculation is fundamental for public health analysis, as it provides a single value that summarizes the central tendency of health-related data, though we must always consider its limitations when interpreting results. There are 3 main types of means used in statistics, each serving different purposes depending on your data and research needs. The simple arithmetic mean gives equal weight to all data points. This is the most common type of average, where we simply add all values and divide by the number of observations. The weighted mean is used when observations have different levels of importance. Each data point is multiplied by its weight, and the formula accounts for these varying weights in the calculation. The geometric mean is specifically used for rates, ratios, and percentages. Instead of adding values, we multiply them together and take the nth root, where n is the number of values. Each type of mean serves a specific purpose. Use the simple arithmetic mean for most basic calculations, the weighted mean when data points have different importance levels, and the geometric mean for rates, ratios, and growth calculations. The mean serves as a fundamental statistical tool across numerous public health applications. From population health assessments to clinical research, the arithmetic average provides essential insights for health professionals and policymakers. One of the most common applications is calculating average body mass index in population studies. Researchers use mean BMI to assess the overall nutritional status and obesity prevalence in different communities. In hypertension research, mean blood pressure measurements help establish baseline values and track treatment effectiveness across patient populations. Blood pressure categories provide important reference points for clinical decision-making. Healthcare administrators use mean hospital stay duration to optimize resource allocation, plan staffing needs, and evaluate treatment protocols. This metric helps hospitals improve efficiency while maintaining quality care. Epidemiologists calculate mean age at disease onset to understand disease patterns, identify high-risk age groups, and develop targeted prevention strategies. This information is crucial for public health planning and intervention timing. The World Health Organization uses mean life expectancy calculations across countries to monitor global health trends and identify regions needing intervention. These statistics inform international health policies and resource allocation decisions. These applications demonstrate the versatility of the mean in public health research and practice. From individual patient care to global health monitoring, the arithmetic average provides essential baseline measurements that guide evidence-based decision-making in healthcare. The mean is a fundamental measure of central tendency with distinct advantages and important limitations that public health professionals must understand. Let's first examine the key advantages that make the mean such a valuable statistical measure. The first major advantage is that the mean uses every single data point in the dataset. Unlike the median or mode, no information is discarded. Second, the mean is algebraically defined, meaning it follows precise mathematical rules that allow for complex calculations and transformations. Third, the mean serves as the foundation for many advanced statistical procedures, including hypothesis testing, confidence intervals, and regression analysis. However, the mean also has significant limitations that can lead to misleading interpretations if not properly understood. The first major limitation is sensitivity to outliers. A single extreme value can dramatically shift the mean away from the typical data values. Second, in skewed distributions, the mean may not represent the typical value. The image shows how the mean gets pulled toward the tail of the distribution, away from where most data points cluster. Finally, the mean cannot be calculated for categorical data. When dealing with non-numeric categories like types of diseases or treatment outcomes, the mean is mathematically undefined. Understanding these advantages and limitations is crucial for public health professionals. The mean is powerful for continuous data analysis, but requires careful consideration of data distribution and the presence of outliers. The median is a fundamental measure of central tendency that represents the middle value in an ordered data set. Unlike the mean, the median provides a robust measure that is not influenced by extreme values or outliers. To find the median, we must first arrange our data in ascending or descending order. The median is then the value that falls exactly in the middle of this ordered list. Here we see an example with 5 data points. First, we arrange them in ascending order, then identify the middle value, which is 11. When we have an odd number of data points, there is a specific formula to find the position of the median. The median is located at position n plus 1 divided by 2, where n is the total number of values. Let's examine a concrete example with 5 values: 59, 60, 65, 68, and 80. Since we have 5 values, n equals 5, so the median position is 5 plus 1 divided by 2, which equals 3. The third value in our ordered list is 65. When we have an even number of values, there is no single middle value. Instead, we take the average of the 2 middle values. For example, with 6 values, we average the values at positions 3 and 4. One of the most important properties of the median is its resistance to outliers. Unlike the mean, extreme values do not affect the median's position. This makes it particularly valuable in public health research, where data often contains outliers. To summarize, calculating the median involves 4 key steps. First, arrange the data in order. Second, count the total number of values. Third, if the count is odd, find the middle position. And fourth, if the count is even, average the 2 middle values. This systematic approach ensures accurate median calculation for any dataset. The median serves as a crucial statistical measure in numerous public health applications. Unlike the mean, the median provides robust insights that are not affected by extreme values, making it particularly valuable in health research and policy decisions. One of the most important applications of the median is in health equity studies, particularly when analyzing household income. Median household income provides a more accurate picture of typical economic conditions than the mean, which can be skewed by very high earners. In cancer research, median survival time is the gold standard for measuring treatment effectiveness. This measure tells us how long half of the patients survive after diagnosis or treatment, providing critical information for patients and healthcare providers. Immunization programs rely on median age at vaccination to understand vaccination patterns and identify optimal timing for public health interventions. This helps ensure maximum population coverage and protection. In disease screening programs, median time to diagnosis helps evaluate the effectiveness of early detection efforts. Shorter median times indicate more efficient screening systems and better patient outcomes. A prime example of the median's practical value comes from the CDC childhood obesity study. Researchers chose median BMI percentile instead of the mean because extreme values in childhood weight data can significantly skew results, making the median a more representative measure of typical childhood health status. These applications demonstrate why the median is indispensable in public health research. From measuring economic health disparities to evaluating treatment outcomes and program effectiveness, the median provides robust, interpretable insights that guide evidence-based public health decisions. Understanding the advantages and limitations of the median is crucial for proper statistical analysis in public health research. The median has unique properties that make it valuable in certain situations while limiting its use in others. The median has three key advantages that make it particularly useful in public health statistics. First, it is not affected by outliers. Second, it can be calculated for ordinal data. And third, it performs better than the mean for skewed distributions. The median remains stable, even when extreme values are present in the dataset. This chart shows how an outlier of 50 dramatically affects the mean, changing it from 14 to 20, while the median stays constant at 14.5. This robustness makes the median ideal for health data that often contains extreme values. Unlike the median can be calculated for ordinal data, where numbers represent rankings or categories. In this patient satisfaction survey using a Likert scale, we can find the median response even though the numerical differences between categories may not be equal. The median tells us the middle response level. In skewed distributions, common in health data like hospital costs or disease duration, the median provides a better representation of the typical value. Here, the mean is pulled toward the extreme values, while the median stays closer to where most data points cluster. However, the median also has important limitations that researchers must consider. It doesn't use all data points, is less suitable for further statistical calculations, and may not be unique in small datasets. The median only considers the middle value or values, ignoring the actual magnitude of other data points. This means valuable information about the distribution is lost, which could be important for understanding the full picture of health outcomes. Many advanced statistical procedures require the mean rather than the median. Standard deviation, confidence intervals, and most hypothesis tests are designed around the mean. This limits the median's usefulness in complex statistical analyses common in epidemiological research. In small data sets with an even number of observations, the median is calculated as the average of the two middle values. This can result in a median value that doesn't actually exist in the dataset, which may be misleading when interpreting results from small clinical studies. Understanding these advantages and limitations helps public health researchers choose the most appropriate measure of central tendency for their specific data and research questions. The median excels with outliers and skewed data, but has constraints in advanced statistical applications. The mode is the most frequently occurring value in a dataset. Unlike the mean and median, the mode focuses on frequency rather than numerical position or average. In this simple dataset, the number 3 appears 3 times, more than any other value. Therefore, 3 is the mode of this dataset. Datasets can have different numbers of modes, which helps us understand the distribution pattern of our data. A dataset can have no mode when all values appear with equal frequency. This often occurs with continuous data or when each observation is unique. A unimodal distribution has exactly one mode, one value that appears more frequently than all others. This is the most common type in many real-world datasets. A bimodal distribution has exactly 2 modes, 2 values that tie for the highest frequency. This often indicates 2 distinct groups or patterns in the data. A multimodal distribution has more than 2 modes. This suggests multiple, distinct patterns or subgroups within the dataset. These histograms visually demonstrate the different types of distributions. Notice how the peaks correspond to the modes. Unimodal has 1 peak, bimodal has 2 peaks, and multimodal has several peaks. This slide reinforces our definition and shows clear examples of each type. Notice how the modes are highlighted in red to make them easy to identify. The mode is particularly useful for categorical data where mean and median cannot be calculated. In these charts, we can identify the most frequent category, the modal category. In the pie chart, the gold section represents 40% of responses, making it the modal category. Similarly, in the bar chart, we can visually identify which category appears most frequently. Understanding the mode and its types helps public health researchers identify the most common responses, behaviors, or characteristics in their data, which is essential for developing targeted interventions and policies. The mode has several important applications in public health research and practice. As the most frequently occurring value in a dataset, it helps identify common patterns that are crucial for health planning and intervention strategies. One of the most practical applications of the mode is identifying the most common blood type in different populations. This information is essential for blood bank management and emergency preparedness. Looking at this global blood type distribution, we can see that type O is the modal blood type in most countries. For example, Peru shows type O as 71% of the population, making it the clear mode for that country. Another important application is identifying peak age groups for disease incidence. This helps public health officials target prevention and screening programs to the most affected populations. In this example of heart disease incidence, the modal age group is 51 to 60 years, highlighted in orange. This information guides screening recommendations and resource allocation for cardiac care programs. The mode is also valuable for identifying the most frequent symptoms in syndrome studies. This helps clinicians recognize common presentation patterns and develop diagnostic criteria. In this syndrome study, fatigue is the modal symptom, occurring in 85% of patients. This information helps establish diagnostic criteria and guides clinical assessment protocols. Finally, the mode plays a crucial role in mental health survey analysis, particularly in depression screening, where modal response categories help identify common symptom patterns. In depression screening surveys, researchers analyze modal response categories to understand common symptom presentations. This helps refine screening tools and identify the most prevalent indicators of depression in different populations. These applications demonstrate how the mode provides valuable insights for public health decision-making, from blood bank management to disease surveillance and mental health screening programs. Measures of dispersion describe how spread out or variable the data points are in a dataset. While central tendency tells us about the typical value, dispersion tells us about the variability around that center. In public health, understanding dispersion is crucial. It reveals health inequalities, helps identify outliers in disease patterns, and informs resource allocation decisions. Two populations might have the same average health outcome, but very different levels of inequality. There are several key measures of dispersion, each with specific uses. The range shows the total spread from minimum to maximum values. Let's examine each measure and understand when to use them. Variance and standard deviation measure how much individual data points deviate from the mean. Standard deviation is simply the square root of variance and is expressed in the same units as the original data. In a normal distribution, standard deviation has special meaning. About 68% of data falls within one standard deviation of the mean, 95% within two standard deviations, and 99.7% within three standard deviations. Quartiles and percentiles divide data into equal parts. Quartiles split data into 4 equal parts, while percentiles can divide data into any number of parts. The interquartile range from the 25th to 75th percentile is a robust measure of spread. Mean absolute deviation, or MAD, measures the average distance of data points from the mean. Unlike variance, it doesn't square the deviations, making it less sensitive to extreme outliers. The Gini coefficient measures inequality in a distribution, commonly used in economics and increasingly in public health. It ranges from 0, indicating perfect equality, to 1, indicating maximum inequality. Each dispersion measure serves different purposes. Range gives a quick overview. Standard deviation works well for normal data. Quartiles are robust for skewed data. MAD handles outliers well, and the Gini coefficient specifically measures inequality. Choosing the right measure depends on your data characteristics and research questions. Range is one of the simplest measures of dispersion, telling us how spread out our data values are. We'll explore two types of range, the simple range and the interquartile range. The simple range is calculated as the difference between the maximum and minimum values in a dataset. It gives us the total spread of our data. Let's calculate the range for this example dataset. The maximum value is 31, the minimum is 12, so our range is 19 units. The interquartile range focuses on the middle 50% of our data. It's calculated as the difference between the third quartile and first quartile. This 5-number summary shows how the interquartile range is calculated. Q1 is 3, Q3 is 13, so the IQR equals 10, representing the spread of the middle half of the data. Range measures have important limitations. This histogram shows a right-skewed distribution with outliers. Notice how the simple range would be greatly affected by these extreme values. The main limitations include sensitivity to outliers, limited information about distribution shape, and reliance on only extreme values. The IQR is more robust but still provides limited insight into the full data distribution. This comparison shows why the interquartile range is often preferred in public health research. While the simple range is easy to calculate, the IQR provides more reliable information about data spread, especially when outliers are present. Range measures provide essential information about data spread, but their limitations must be considered when analyzing public health data. The choice between simple range and IQR depends on your data characteristics and research objectives. Variance and standard deviation are fundamental measures that tell us how spread out our data points are from the center. While measures of central tendency show us the typical value, variance quantifies the variability around that center. Variance measures the average of the squared deviations from the mean. We square the deviations to ensure that positive and negative differences don't cancel each other out, and to give more weight to larger deviations. For population variance, we use the formula sigma squared equals the sum of x minus mu squared divided by n. Here, sigma squared represents the population variance, x represents each individual data value, mu is the population mean, and n is the total number of values in the population. For sample variance, we use a slightly different formula. Sample variance equals the sum of x minus x bar squared divided by n minus 1. The key difference is that we divide by n minus 1 instead of n. This adjustment, called Bessel's correction, provides an unbiased estimate of the population variance from sample data. Standard deviation is simply the square root of the variance. While variance is measured in squared units, standard deviation returns to the original units of measurement, making it much easier to interpret. For population standard deviation, we use sigma, and for sample standard deviation, we use S. To visualize the concept of variance, consider these two distributions. Both have the same mean, but distribution A has higher variance. Its data points are more spread out. Distribution B has lower variance. Its data points cluster more tightly around the mean. Here's another example showing two normal distributions with the same mean but different standard deviations. The red curve has a standard deviation of 10, making it wider and flatter. The purple curve has a standard deviation of 5, making it taller and narrower. This demonstrates how standard deviation directly relates to the spread of the distribution. Understanding variance and standard deviation is crucial for public health research. These measures help us quantify the variability in health outcomes, assess the consistency of interventions, and identify populations with high health disparities. Understanding how to interpret standard deviation is crucial for public health analysis. For normally distributed data, we can use the empirical rule, also known as the 68-95-99.7 rule. This rule tells us that in a normal distribution, approximately 68% of data falls within one standard deviation of the mean, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. Now, let's explore the coefficient of variation, a powerful tool that allows us to compare variability between different data sets, even when they have different means or units of measurement. The coefficient of variation is calculated as the standard deviation divided by the mean, multiplied by 100 to express it as a percentage. This standardized measure allows meaningful comparisons across different scales. Let's see why the coefficient of variation is so useful with a practical example. Imagine comparing the variability of blood pressure measurements versus body weight measurements in a health study. Without the coefficient of variation, we might think blood pressure is more variable because its standard deviation is higher. However, the CV reveals that body weight actually has more relative variability at 14.3%, compared to 12.5% for blood pressure. A real-world application comes from a recent global vaccine distribution study. Researchers used standard deviation of vaccination rates across countries to measure global health inequity. The study found that vaccination rates had a high standard deviation across countries. indicating significant global inequity. This statistical measure helped policymakers identify the need for targeted resource allocation to improve global vaccine access. Understanding standard deviation interpretation and coefficient of variation is essential for public health professionals. These tools help us quantify variability, compare different data sets, and make informed decisions about health interventions and resource allocation. Beyond basic measures like range and standard deviation, advanced dispersion measures provide deeper insights into data distribution and inequality. These measures are particularly valuable in public health for understanding population variations and health disparities. Percentiles divide a dataset into 100 equal parts. The 25th percentile means 25% of data falls below this value, while 75% falls above it. In public health, percentiles are used in growth charts for children, reference ranges for laboratory values, and population health assessments. For example, a child at the 75th percentile for height is taller than 75% of children their age. Quartiles are special percentiles that divide data into 4 equal parts. Q1 is the 25th percentile, Q2 is the 50th percentile or median, and Q3 is the 75th percentile. The interquartile range, or IQR, is Q3 minus Q1. This measure contains the middle 50% of the data and is resistant to outliers, making it valuable for describing spread in skewed health data. Mean absolute deviation, or MAD, measures the average distance of data points from the mean. Unlike standard deviation, MAD is less sensitive to extreme values, making it a robust measure of dispersion. MAD calculates the absolute differences between each data point and the mean, then averages these differences. This approach treats all deviations equally, regardless of direction, and reduces the impact of outliers compared to standard deviation. The Gini coefficient measures inequality in a population, with values ranging from 0 to 1. A value of 0 represents perfect equality, while 1 represents maximum inequality. In public health, it's used to measure health disparities across populations. In health equity research, Gini coefficients help identify disparities in healthcare access, health outcomes, and resource distribution. For example, a Gini coefficient of 0.3 for healthcare spending indicates moderate inequality, while 0.7 suggests severe disparities requiring intervention. These advanced dispersion measures provide public health professionals with sophisticated tools for understanding population health patterns, identifying inequalities, and making evidence-based decisions for health interventions and policy development. Graphical presentations are essential tools in public health statistics for visualizing data patterns, distributions, and outliers. We'll explore 4 key types of graphical presentations that help researchers and practitioners understand their data effectively. Histograms display frequency distributions by dividing data into bins and showing how many observations fall within each range. They're excellent for understanding data shape, identifying skewness, and spotting potential outliers. Box plots, also called box and whisker plots, provide a 5-number summary of data: minimum, first quartile, median, third quartile, and maximum. They excel at showing data spread and identifying outliers beyond the whiskers. Violin plots combine the information of box plots with kernel density estimation, showing both the summary statistics and the actual shape of the data distribution. They're particularly useful for comparing distributions between groups. Dot plots, also called strip charts, display individual data points along a single axis. They're excellent for small to medium data sets where you want to see every observation and easily identify outliers or clusters. Here's a practical example comparing groups using box plots. This chart shows age distributions of Oscar-winning actors by gender, clearly displaying differences in central tendency, spread, and outliers between the two groups. Each graphical presentation method serves specific purposes in public health research. Choose histograms for distribution shape, box plots for summary statistics and outliers, violin plots for detailed distribution comparisons, and dot plots when individual data points matter. Tabular presentations provide structured, detailed numerical summaries of data. In public health research, we use 3 main types of tables to organize and present our findings effectively. First, frequency tables summarize categorical data by showing how often each category appears. These are essential for understanding the distribution of qualitative variables in health studies. Frequency tables show both absolute counts and relative percentages, making it easy to understand the proportion of each category in your dataset. Second, summary statistics tables organize key descriptive measures for continuous variables. These tables present central tendency and dispersion measures in a clear, organized format. These tables allow researchers to quickly compare multiple variables and their statistical properties, making them invaluable for research reports and publications. Third, cross-tabulations, or two-way tables, explore relationships between two categorical variables. These tables are crucial for identifying patterns and associations in public health data. Here's an example of a cross-tabulation examining the relationship between age groups and frequency of healthcare visits. Notice how the table shows both counts and percentages for each combination. Cross-tabulations reveal important patterns. For instance, we can see how visit frequency varies across different age groups, helping identify which populations may need targeted health interventions. Tabular presentations provide the detailed numerical foundation that supports data visualization and statistical analysis. They ensure transparency and allow readers to examine the exact values underlying research conclusions. When analyzing public health data, choosing the right statistical measures is crucial for accurate interpretation. We need a systematic decision framework to guide our choices. For central tendency measures, we start by examining the distribution type. This determines which measure will best represent our data. If our data follows a normal distribution, the mean is the best choice as it uses all data points and provides the most information. For skewed distributions or data with outliers, the median is more appropriate because it's not affected by extreme values. For categorical data, the mode is the only meaningful measure of central tendency, representing the most frequently occurring category. Let's see these concepts in action. Here's a normal distribution where the mean would be most appropriate. In contrast, here are skewed distributions where the median would be more representative than the mean. For dispersion measures, we also consider distribution type, but we must also think about the purpose of our analysis. For normal distributions, standard deviation is ideal because it provides precise information about data spread around the mean. For skewed distributions, the interquartile range is more robust and less affected by extreme values. When comparing different groups or studies, the coefficient of variation allows meaningful comparisons by standardizing the measure. Here's a box plot showing the interquartile range, which is perfect for describing dispersion in skewed data. The coefficient of variation formula allows us to compare variability across different scales and units of measurement. Remember, the key is matching your statistical measure to your data characteristics and research objectives. This systematic approach ensures accurate and meaningful analysis in public health research. Public health statistics is rapidly evolving with emerging technologies and a renewed focus on equity. 4 major trends are reshaping how we collect, analyze, and interpret health data. First, big data analytics is transforming public health surveillance. Modern health systems generate massive data sets that require new statistical approaches for real-time monitoring and analysis. Streaming statistics enable continuous health monitoring, processing data as it arrives from hospitals, clinics, and surveillance systems. This allows for immediate detection of disease outbreaks and health emergencies. Robust statistical measures help handle data quality issues common in large data sets, ensuring reliable analysis despite missing values, measurement errors, and inconsistent data sources. Automated outlier detection systems can identify unusual patterns that might indicate disease outbreaks, data errors, or emerging health threats without human intervention. Second, there is an increased focus on health equity. Public health professionals are using dispersion measures to identify and address health disparities across different population groups. Dispersion measures like standard deviation and interquartile range are being used to highlight health inequalities between racial, ethnic, and socioeconomic groups. Intersectional analysis examines how multiple factors like race, gender, and income interact to affect health outcomes, requiring sophisticated statistical approaches. Geographic information systems integration allows researchers to map health disparities spatially, revealing patterns of inequality across neighborhoods and regions. Third, Precision medicine is revolutionizing healthcare by focusing on individual level variation rather than population averages. This requires new statistical approaches to analyze personal health data. Individual level variation analysis examines how treatments and outcomes differ between patients. Moving beyond population means to understand personal responses. Personalized reference ranges replace standard population norms with individualized baselines based on genetic, lifestyle, and environmental factors. Biomarker distribution studies analyze how biological indicators vary across individuals to identify optimal treatment strategies for specific patient subgroups. Finally, digital health integration is creating new data sources that require innovative statistical approaches. Wearable devices, mobile apps, and remote monitoring generate continuous health data streams. Wearable device data summarization involves processing millions of data points from heart rate monitors, step counters, and sleep trackers to extract meaningful health insights. Continuous monitoring statistics help identify trends and patterns in real-time health data, enabling early intervention and personalized care recommendations. Patient-reported outcomes analysis combines subjective health assessments with objective measurements, requiring statistical methods that can handle mixed data types and varying reporting frequencies. These four trends represent the future of public health statistics, where traditional measures of central tendency and dispersion are enhanced by new technologies and a commitment to health equity for all populations. We'll examine a comprehensive case study analyzing the COVID-19 vaccination campaign across all 50 United States. This real-world example demonstrates how measures of central tendency and dispersion provide crucial insights for public health policy. The analysis revealed three key statistical measures. The mean vaccination rate across all states was 68.5%. The median rate was slightly higher at 70.2%. The standard deviation was 12.3%, indicating moderate variability between states. This map visualizes the vaccination rate variations across states. Darker colors represent higher vaccination rates, while lighter colors show lower rates. We can clearly see the geographic disparities that contribute to our calculated standard deviation. The statistical interpretation reveals several important insights. Since the mean is less than the median, we observe a slight negative skew in the data. The 12.3% standard deviation indicates moderate variation between states. Using the mean plus or minus 2 standard deviations, we estimate vaccination rates ranged from approximately 44% to 93% across states. These statistical findings have direct policy implications. Health officials should target low-performing states with additional resources and investigate the underlying factors causing disparities. Tailored intervention strategies can address specific state needs. The ultimate success metric would be reducing the standard deviation over time, indicating more consistent vaccination rates across all states. This case study demonstrates how measures of central tendency and dispersion transform raw vaccination data into actionable public health insights. By understanding both the average performance and the variation around that average, policymakers can make informed decisions about resource allocation and intervention strategies. We've covered essential statistical measures for public health. Now, let's consolidate the key takeaways that will guide your practice as public health professionals. First, and most importantly, context matters. The choice of statistical measures depends entirely on your data type and distribution shape. Second, never rely on a single measure. Use both central tendency and dispersion measures together for a complete understanding of your data. Third, visual presentations communicate statistical information far more effectively than numbers alone. A well-designed graph can reveal patterns that tables of numbers cannot. Fourth, dispersion measures are crucial for identifying health inequalities. Standard deviation, range, and other dispersion measures reveal disparities that averages alone cannot show. Finally, big data and digital health technologies require robust statistical approaches. Traditional measures remain foundational, but we must adapt to handle the volume and complexity of modern health data. These statistical measures are your foundation for evidence-based public health practice. Master them, apply them thoughtfully, and use them to improve population health outcomes and reduce health disparities.